Hi friends, so welcome to the topic of chemical kinetics today is our first lecture. Today we will be dealing with the introduction on chemical kinetics, our rate equation, order, molecularity, etc. So as you know, we chemists always deals with chemical reaction. What is a chemical reaction? A chemical reaction is something in which there is a transfer of electrons. This transfer or movement of electrons may be within the molecule or it can be from one molecule to another molecule. Whatever it may be, we always deal with this transfer of electrons. These transfer of electrons or the speed at which this transfer of electrons is happening has got profound influence in our daily life. Let us see what are those most important aspects of the chemical kinetics. An organic chemist can identify his mechanism or he can confirm his mechanism through chemical kinetics. Whereas a chemical engineer can go for a reactor designing after the proper study of chemical kinetics. Even in a pharmaceutical research, a pharmaceutical researcher can design a proper molecule that will give a proper drug interaction with the human body. In these aspects, study of chemical kinetics is a very important aspect. So in chemical kinetics, actually what are we dealing with? We are dealing with the rate of change of concentration with time. So in that aspect, we have two important points to consider. One is extent of reaction. The concept was given by T. Dolder. And the second one is the rate of reaction. Rate of reaction. Mostly we will be dealing with the rate of reaction. But for a proper understanding of chemical kinetics, we should know what you mean by the extent of reaction. Extent of reaction can be given by a very simple equation, which is epsilon is equal to n minus n0 by nu, where n0 is the initial amount of moles, n is the final amount of moles, and nu is the stoichiometric constant. So let us go for a general reaction which is given as AA giving AA plus B moles of B giving you X moles of X and Y moles of Y. For this reaction, how can we write the extent of reaction? The extent of reaction can be given as epsilon is equal to delta NA divided by minus A. So this delta Na is nothing but n minus n0 and this A is the nu, the stoichiometric coefficient. So delta Na by A is equal to delta NB by B, which will be equal to delta Nx divided by X, which again will be equal to delta N capital Y divided by Y. The most important aspect of the extent of reaction is that when you calculate the extent of reaction, you will see that it will be same for all the participants. Here we have got 4 participants which are A, B as the reactants and also X and Y as the products. For all the participants, the extent of reaction will be same. The first concept which we explain, the extent of reaction, it is actually time independent concept. That means this is considered for the total reaction time. Whereas we are going for the to explain the next one, rate of reaction, which is actually time dependent. So we can see rate equation is time dependent. Let us try to draw a graph in which a reaction is happening, a simple hypothetical reaction in which A is giving you B. Let us monitor this reaction. Generally in chemical kinetics, we will be monitoring a chemical reaction using a concentration and time graph. The concentration time graph will be plotted as this, in which the x-axis we will be plotting time, whereas on the y-axis we will be plotting concentration. This can be in moles liter minus 1, and this may be in normally in seconds, sorry, in seconds. Now, if you see from the reactant side, the reactant concentration will be initially high, somewhere around here, and slowly the reactant concentration will decrease. So this is for the reactant A. And if we go to the side of the products, you can see that initially the product amount will be less, but slowly the product amount will be increasing. So this is an ideal concentration time graph. There are some important points to consider here. As you know, here if you check from the reactant side, initially the rate of change of concentration is very high. That means the slope of this curve is very high. If we take a dy by dx here, we will be having a very high value, whereas here the dy by dx will be a low value. Similar is the case of the product side also. In the initial side here you can see there will be a high dy by dx, whereas here the slope will be less. So what does that mean? The rate of the reaction is not a constant throughout the reaction. It is changing continuously, but it is having a very special trend. It will be very high. The rate of change of concentration will be very high at the initial level, and slowly it approaches a constant value. And also for the products also, the rate of appearance of product B will be a high value initially, and slowly it will be reaching almost a constant value. So this is general for any concentration time graph. So from this graph, let us try to have an expression for the rate of reaction. As we know, at T equal to 0, the concentration of A will be maximum, and let us see what will be happen at T equal to T1. Let it the concentration of A be A1. And if it is so, the concentration of B is B1. And at T equal to T2, concentration of A is A2 and concentration of B is B2. Now, as we know, the rate of reaction is defined as the change in concentration divided by time. Presently, we are going to see an expression for average rate of reaction. So we can see, now we are going to study what is an average rate of reaction. So in this aspect, as we see, what will be the average rate of reaction for A? So average rate of reaction, let us give it is as mu average will be equal to A2 minus A1 divided by T2 minus T1. A is the reactant, as you know. A2 will be, if you try plot T1 here and T2 somewhere around here, you will see that the concentration of A will be here at here, and this place will be at here. And as our average will be equal to A2 minus A1, this will be a negative quantity and this will always be a positive quantity. So that is the average rate of reaction for A within the time limits T1 to T2. What will be for B? So we can write as our average in terms of, here it is for A, this is for B, will be equal to B2 minus B1 divided by T2 minus T1. Once you check from the graph, you can see that always B2 will be higher than B1 and this will be having a positive quantity. So this will be always, this will be a negative quantity and this will be a positive quantity. Now, one more aspect we have to see is for a general reaction which we had written before, which was AA plus BB plus, giving you XX plus Y. The average rate of reaction can be given as, here I am writing the expression for rate of reaction here as average is equal to minus 1 by A. Instead of writing A2 minus A1, I am going to write it as delta A divided by delta T, which will be equal to minus 1 by V, delta V by delta T, which again will be equal to plus 1 by X, delta X by delta T, which again will be equal to plus 1 by Y delta Y by delta T. So that is about the average rate of reaction. Now let us see what we mean by empirical rate equation, order of a reaction, and molecularity of a reaction. So the rate can be expressed as rate is proportional to concentration of A times concentration of B. This is for a very simple reaction in which A plus B is giving you the products. So rate is proportional to concentration of A and concentration of B. We can write with an equality sign. Rate is equal to a constant multiplied by concentration of A and concentration of B. This constant K is called as rate constant. Now, in practice, actually when we are writing rate is proportional to concentration of A and B, we have to know that it is actually rate is proportional or rate is equal to K into concentration of A to the power of some exponent alpha and concentration of B to the power of some exponent beta, where rate alpha and beta, where the exponents alpha and beta are called as partial orders of the reaction. So alpha and beta are called as partial orders. And the sum of alpha and beta, alpha plus beta is equal to n, which is called as the order of the reaction. So order of the reaction can be denoted as n. So for this reaction, if you are writing the order, we can write as rate is equal to K into concentration of A to the power of 1 and concentration of B to the power of 1. Here we are meaning to say alpha is equal to 1, beta equals 1, and n is equal to 2. So this reaction is a second order reaction. Now going to a very one more simple step. If you are going for a reaction of A giving B, this order of this reaction will be, or the rate equation can be given as R is equal to K into concentration of A to the power of 1 and order of the reaction is equal to 1. Now let us see the concept of molecularity of a reaction. For that, let us consider a complex reaction like decomposition of nitrogen pentoxide, where 2N2O5 plus 4NO2 is giving you. So 2N2O5 is decomposing to 4NO2 and oxygen. Actually, this reaction is happening in 3 different steps, in which N2O5 is giving NO2 plus NO3, NO plus NO3 giving NO2 plus O2 plus NO, and one more reaction in which NO plus N2O5 giving you 3NO2. In these reactions are called as elementary reactions. So meaning to say, these elementary reactions are constituting towards the complex reaction of the decomposition of nitrogen pentoxide. And in this case, we mean the molecularity is the number of molecules taking part in each elementary step. So you can see in the first step here N2O5 is decomposing and the number of molecule is only 1. So this is the molecularity of this reaction is only 1. Whereas in this reaction you can see NO is reacting with NO3 and so that the molecularity of this reaction is 2. Again, in the last step also you can see that there are 2 molecules reacting in the elementary reaction so that the molecularity is again 2 for this particular elementary reaction. So meaning to say molecularity will be always having an integer values. It won't have it having a 0 values or fractional values. Whereas order, which is an experimental quantity, can have zero or fractional values and also integer values.